Okay, so our next speaker is Davide Scaramuzza. He's a professor of robotics and perception at the University of Zurich. His research focuses on autonomous, agile navigation of micro aerial vehicles using standard and event-based cameras. He has won many awards, including the very recent IEEE Technical Field Award. He also won the IEEE RAS Early Career Award and many paper awards, including the IROS 2023 Best Paper Award, and the RAL Letters and IEEE Transactions Best Paper Awards. Welcome.
Thanks a lot, Nancy. It's really an honor to be here. I won't be talking about drones today. I will be talking about event cameras and their promise for robotics, hopefully. So this talk is about agile robotics, from cameras to neuromorphic sensing. Let's review very quickly the state of the art of agile robotics over the past few years. So thanks to perception, we have witnessed incredible leap forwards in the last 10 years, from legged robots doing parkours, but there is still a lot to actually win in terms of robustness and latency, up to drones that were able actually to even outperform world champions in drone racing just using an onboard camera. Still, when you compare the performance of the best robots against the state-of-the-art, you can see that we still have a long way before we can reach human-level performance. Same goes to also manipulation. This is impressive work from Stanford about agile manipulation with 2 arms, but there is still a lot of work to reach kind of the level of human-level performance. So when you look at the past 60 years of computer vision, you notice that actually the research has been dominated by standard cameras. But I argue that they are not good enough because they suffer from motion blur, low dynamic range, and they have actually a bandwidth latency trade-off. What is that? So if you want to increase the agility of a robot, you actually must lower the latency of its sensors and algorithms. And at the moment, if you want to actually achieve a low latency with a standard camera, you are obliged to increase the frame rate. But by increasing the frame rate, you increase the bandwidth of the system, which is not ideal because on many platforms, it's impossible to put an unlimited compute. So for a standard camera, you are bounded to the so-called bandwidth latency trade-off hyperbola, because the bandwidth is inversely proportional to the latency that you want to achieve. Well, there is a sensor that allows you to achieve arbitrary bandwidth at an arbitrary latency. That sensor is the event camera. What is the event camera? The event camera is a camera that measures only motion in the scene. So whether there is motion of the camera or relative motion between the camera and the scene. It achieves so by using smart pixels that are all independent of one another. Whenever a single pixel detects motion caused by change of brightness at the pixel level, that pixel triggers an event. So the output of the event camera is not frames at constant time intervals, but rather a stream of asynchronous events. What I want you to remember is that these events are continuously streamed. But there is a bottleneck. The bottleneck is that you cannot apply the traditional computer vision algorithms that have been developed for the past 60 years of research. So you need to come up with new algorithms in order to adapt them to the asynchronous nature of this sensor. But the interesting thing, and that's why I'm here today, is because event cameras unlock scenarios that are inaccessible to standard cameras, from legged robots, flying robots, and even manipulation. So let's start with the backbone of mobile robotics, state estimation, also called SLAM. We showed a few years ago that if you use an event camera, you can actually combat motion blur. Here, my student is spinning the event camera thanks to its USB cable. So we firmly attach the USB cable to the camera and we spin it as a cowboy. You can see that the output of the standard camera is strongly motion blur, so you cannot do SLAM. But you can do it with the event camera. You can estimate the motion and the map of the environment. A few years later, Davide Falanga showed that thanks to the event camera, you can enable high-speed dodging of dynamic objects with an incredible latency of 3.5 milliseconds. This means that you can possibly achieve this with a standard camera, of course, but you need 3.5 milliseconds latency. That means you need at least a 250 FPS camera. How are you going to process all those frames in real time? Instead that you want a higher frequency, how would you do it? That's the key advantage of the event camera. Low bandwidth, a very low latency. More recently, with my colleague Marco Utter at ETH, we showed that you can even catch objects thrown at the robot. More recently, the groups of Giorgia Chalvasaki, Roberto Calandra, and Jan Peters, they showed that event cameras allow, for example, a new type of optical tactile sensing with latency similar to that of humans, 1 milliseconds. So an update rate of 1,000 hertz. Again, low bandwidth, a very, very low latency. That's the key advantage. And they show they can do closed-loop control, including sleep detection and sideways grasping. So here the object, for example, suddenly sleeps, and the tactile sensor is able to retrieve it immediately with no perceivable latency, similar to human hands. Let's move to industry. A collaboration between Stratava and Boeing has shown that event cameras can also be used to increase the inspection task by a factor of 10. So here, at Stratava in Abu Dhabi, they do production of Boeing wings. What you see here in yellow is a mock-up wing with multiple holes called countersinks. Typically, the inspection is done with a standard camera that poses in front of each hole to enable the detection and the measurement of the diameter and the depth of the countersink. But now with the event camera, they showed that you don't need to stop at all. You can just swipe the event camera in front of it, increasing the inspection time by a factor of 10. Okay, now let's recap the last 10 years of research on event cameras. Well, actually, they were dominated by single cameras, single event cameras. But actually, what I believe is going to happen, and it's already happening, is the combination of event cameras with frame-based cameras. Right, because the two sensors are actually complementary. Standard cameras are low-pass filters, event cameras are high-pass filters. They only convey the varying component of the visual signal. And the human brain is actually an incredible inspiration because we have slow, fast pathways in our brain. We have also different photoreceptors with different reaction times, rods and cones, one for slow motion things and the other one for high reflex and reactive navigation. So what I think we are going to witness, and it's already happening in the future for robotic control, is the coexistence of two different sensors with slow-fast cognitive levels, what I call a hybrid asynchronous control architecture, where we have a slow cognitive level that processes images coming from standard cameras, and we have a fast cognitive level that processes information from event cameras and provides, ideally, control commands at the resolution of single events. We have already preliminary results using this hybrid architecture applied to object detection for automotive, so to increase the safety of current automotive systems, including autonomous driving. You see on the left a standard camera stream, and on the right the continuous output of the event camera. And here is our proposed solution, where we have a synchronous CNN that processes frames at low frame rate, so the cognitive is low level, and then we have an asynchronous graph neural network that processes events at the resolution of single events, but shares embedding with a CNN, providing, therefore, high-level, high-frequency update object detections. This result was recently published in Nature and mentioned on the cover, and what it enables to do is inter-frame object detection, realizing that there is a traffic participant, a car, a bicycle, a truck, a pedestrian in front of the car much faster than a standard camera. And if a frame detection is available, then you can keep the performance of the object detection from the last frame very high until the next frame becomes available. The key finding of this research is that we showed that if you use a 20 frames per second camera plus an event camera, you can achieve the same latency as a 5,000 frames per second camera, but with a bandwidth of a 50 FPS camera without compromising accuracy. So we can lower the bandwidth and the latency by a factor of 100. And I think this can have a huge impact. So going back to the field of event vision, What has been done and what's the future ahead? Event cameras were invented in 2008 by Professor Toby Delbruck at the University of Zurich, but the pixels were very high, very large, 40 microns. Only 6 years later, the first event camera became commercially available, so we were able to finally purchase it. In 2019, Apple and Facebook started patenting a lot of event camera patents. In 2021, Sony, Samsung, and OmniVision, which are the three top camera manufacturers, starting putting a lot of money in event-based vision. In 2022, Meta opened their first event-based sensing labs. ESA sent to space 3 event cameras between 2023 and 2024 for Sprite and high atmosphere phenomena detection, star tracking, and also space debris collection. And last year, the event camera company Prophecy and Qualcomm announced a multi-year deal to put event cameras on smartphones. So there is still a lot to apply. I hope this talk was inspirational, and I would like to thank my incredible team and to you for your attention. Thank you.
So we can take a few questions, and we can also start switching out to the next speaker. If you have a question, it's hard for us to see.
I think Catherine there.
Oh, maybe, here's one.
Oh, yeah.
Am I on?
Yes.
Davide, thank you for the beautiful talk. I'm very convinced, but how do you disambiguate events caused by self-motion from events of objects moving in the environment?
Indeed, very good question. Because the event rate relates to the relative speed and the gradient of the texture. So you can actually analyze the temporal statistics of the events to figure out which events are caused by the stationary background, so ego motion of the vehicle, or self-motion. We use a framework called the contrast maximization framework that basically analyzes these different temporal statistics. So you don't even need machine learning for that.
Show 8 minutes. Another question. Oh, here's one, right here.
Darius.
Thanks for the great talk. My question is similar to the other one. You have the low latency just because you have sparse events. So how does it work actually if all the pixels vote for some change? So you lose your bandwidth in this case.
Indeed. So I usually bring up the example, what happens if you turn on or off the light? Well, then in principle, all the events would trigger. Well, yes, you would actually observe a sinusoid that goes up and down beautifully. So that's the temporal resolution of the event camera. It depends on the type of light that you're using. So in principle, it's very difficult to saturate all the events. But let's see where you're going. So what happens if everything is moving and every pixel triggers information? In this case, what you can do is to modulate the contrast sensitivity of the event camera that decides when an event is generated, because an event is generated whenever the brightness change passes a threshold, and this depends on the relative speed and the magnitude of the gradient. So by modulating it, basically you are giving priority to stronger edges. So you will never have that situation. And by modulating the contrast sensitivity, you also can cap the bandwidth.
Okay, well, thank you very much, Davide. Let's give him another
Thank you.
hand.
Thank you very much.